Hi y'all, it's time for something new. We're going to talk about temperature, kinetic theory, and the gas law. We are building up to something big when we talk about thermodynamics, but in order to get there, we have to build up some tools first. So we've talked about fluids, and fluids will be key to doing stuff with thermodynamics, but the other part to thermodynamics is the thermo part. Temperature is involved. So in case you hadn't noticed, physics thus far has been built out of length, time, and mass. I think that's it. Length, time, and mass, and we've mixed and matched them together in a bunch of different ways. We've talked about momentum, and we've talked about kinetic energy and joules, but joules and newtons are all just mashing together different concepts with mass, length, so for a velocity is meters per second, that's length over time, length, time, so all of those things are all kind of mashed together concepts with those three things. So now something new, temperature. Hey, wild. All sorts of things go on with temperature. We measure temperature using things called thermometers. We have some different concepts that we can do here. I think I come up to a point here. Yes. Temperature is a measure of how hot or cold something is. Now, this is a distinction we have to know. Temperature is not energy, nor is temperature heat. We'll do more on this later, but temperature is a measure of the motion, the vibration or translation of atoms or molecules that make up a substance. So if you have greater motion of the atoms and molecules, then it's a greater temperature. If you have smaller motion, then it's a lower temperature. There's three common scales for temperature: Fahrenheit, Celsius or centigrade, and then Kelvin. All right, so turns out we had Isaac Newton and Newton's laws. There were three laws, right? Now it turns out in the world of thermodynamics, they thought, wow, this is great. We'll have three laws of thermodynamics. And so we do. We have the three laws of thermodynamics. We'll talk about those later on. But it turns out on the way they left off something that was pretty important. So we're going to call that the 0th law of thermodynamics. Before we can define that, let me tell you that there's this thing called heat. This is going to be Q. Heat is energy that is transferred between objects. And why that energy is transferred is because objects have a different temperature. So when you pick up that hot mug of coffee, the coffee is hot, it's warmer than your hand is, and then you can feel heat being transferred into your hand. If you pick up a warm, a room temperature glass of water or soda or something, you don't feel any temperature being transferred, any heat being transferred, because it's at the same temperature as your hand. So that's the thing. That hot mug of coffee that's sitting across the table from you, no heat is flowing because you're not in thermal contact with it. You have to touch it. There has to be a mechanism for heat to transfer between the two objects that are two separate temperatures. And then when the transfer of heat between objects in thermal contact ceases, it ceases because they are in thermal equilibrium, and thermal equilibrium will be the condition at which they are at the same temperature. Alright, so that brings us to the 0th law of thermodynamics, which says that if object A is in thermal equilibrium with object B, and object C is also in thermal equilibrium with object B, then objects A and C will be in thermal equilibrium if they are brought into thermal contact. That is to say that temperature is the only factor that determines whether two objects in thermal contact are in thermal equilibrium or not. So this is basically saying object B is a thermometer. And if I put object B into thermal contact with object A, that thermometer will read a certain value. And then I hold it up to object C and it reads the same value. And so I know that if I chose to bring objects A and C together that no heat would flow between them. I'd be able to say, hey, those two things, I can know that heat won't flow between them because they're at the same temperature. And this allows me to measure temperature using some object. So the common temperature scales, the Celsius scale, water freezes at 0 degrees Celsius and boils at 100. The Fahrenheit scale, water freezes at 32 and boils at 212. The Fahrenheit scale is a really weird one. Fahrenheit was a German chemist, physicist, German scientist. He did some chemical reactions with reactions that were endothermic, so like an ice pack that you might get where you smash it together and the chemicals mix and it gets cold. There's some chemical reactions that do that. He did that with some chemical reactions, and he called 0 degrees the coldest temperature he could make in his lab. And then he decided to call the upper limit, the higher temperature, body temperature, which he called 96 degrees, which I guess he was a cold man. So that's how the Fahrenheit scale is designed. The degree size in Fahrenheit, if you look 32 to 212 for water freezing and boiling, the degrees are big. They're almost 2 degrees Fahrenheit for every 1 degree Celsius. So that's what Fahrenheit did. Celsius came along and we're in the condition where water freezes at 0 degrees Celsius and boils at 100, and there's 100 degrees in that scale from water freezing to boiling, and Celsius thought that was a good good material to use to define his scale, and that's what we have for Celsius. You can convert between Celsius and Fahrenheit. The equations are here. It might be relevant for some applications. Typically, scientists just stick with Celsius or more often Kelvin. We'll talk about Kelvin next, but if you need to convert from one to the other, here are our equations, and we can plug in the unknown and figure out the known, and there's a skill you'll have. Now, it turns out that if you take a gas in a confined cylinder and measure its pressure when it's submerged in boiling water at 100 degrees Celsius, it would record a certain pressure. And if you took that and you stuck it in ice water, it would record another pressure. Well, if you connect the dots for those 2 points and extrapolate down to 0, there is a temperature which matches up to this thing that we're going to call absolute zero. There's a lowest temperature. Temperature is a scalar quantity, not a vector quantity. So the negative sign that we sometimes have for temperatures is arbitrary, based on ice freezing at 0, or the weird world of Fahrenheit where ice freezes at 32, but you can still get much colder than that and get into negative temperatures. But it's not really a negative temperature. It's 0. So in Kelvin, we're going to use the same degree size as Celsius, but start at absolute 0 and go up from there. Now, this is important because in certain equations that we have moving forward, say like the ideal gas equation, that's PV equals nRT. Well, in that case, T is in Kelvin. It's the absolute temperature. Other equations that we'll use will include delta T, the change in temperature. If it's the change in temperature from 100 degrees Celsius to 0 degrees Celsius is 100 degrees. The change in temperature from 373 degrees Kelvin to 273 Kelvin is 100 degrees. So in that case, delta T, it doesn't matter whether we do Celsius or Kelvin. However, vitally important, if we are using an equation that just has T in it, not delta T, then you must have the temperature in Kelvin or you will get the answer wrong. So you can look at the temperature scales as they compare to each other. There they are again. Okay, linear thermal expansion. I'm going to take a break and then we'll come back to